All right, we're going to do a quick summary of what happened in class. This was our warm-up, and at any point, stop and pause if you'd like to think about anything a little more. This is our warm-up. Then we got our quizzes back. We went over the homework assignment for today. And then we began taking notes on section 9.2. First, we defined an infinite series. We defined partial series. We talked about the notation. If you see a capital S, that means the sum of the infinite number of terms. We talked about the definition of a converging series. The big question of the unit is, does the series converge or diverge? And if it converges, then to what? So it often is helpful to expand. Expanding can help us to deduce the pattern. We'll start with this series. This series is 1/2 plus a 4th plus a 8th plus a 16th. If we have a 1 by 1 square and we shade in a half of the square, then a half of the remaining half, which is a 4th, then a half of that 4th, which is an 8th, and keep on doing halves, we'll fill in the square. This series should converge to 1. We also know that if you're always multiplying times a half, times a half, times a half, that it's a geometric series where the first term is 1/2 and the common ratio is times a half. And we derived the formula last week that if you know the first term and the common ratio, the first term divided by 1 minus the common ratio will be equal to the infinite sum of the series, which in this case is 1. All right, here's another example, n squared plus n. Well, expanding it doesn't really help. We can see a pattern, up 4, up 6, up 8, up 10, up 12 for the denominators, but how can we tell what it's converging to if it's converging? Well, just as a fraction like 1/6 can have its denominator factored in the 2 times 3, and we can rewrite this as a decomposition into several partial fractions, we can do the same thing with 1 over n squared plus n, our expression. But first we'd want to factor this into this expression. And so 6 is factored in the 2 times 3. Take each factor, write a separate fraction for each of those factors, or in this case, a separate fraction for the factor n and a separate fraction for the factor n plus 1. Get rid of the denominators by multiplying by the product of those two factors. It'll be completely gone on the left. We'll have to distribute on the right. That leaves us with a, and the n's cross off, so a times n plus 1 and b times n. We need to know what a and b is. If we're trying to decompose this fraction algebraically, we need to know what a and b is, what a and b are. So if we let n equals 0, then b times 0 is 0. 0 plus 1 is just 1. So a times 1 is just a, and a plus 0 is equal to 1. A is 1. If we let n equal -1 in this equation, then we have 1 equals a times -1 plus 1, which is 0, plus b times -1. Or just negative b is 1, so b is -1. All right, so we know what a and b are, so we can rewrite this expression as the a value over n plus the b value over n plus 1. So this summation is now the sum of a over n plus b, which is plus a -1 over n plus 1. Expand. When we expand, the -1/2 and the +1/2 cancel each other out. The yellow, these third and negative third terms cancel out. The fourths cancel out. Everybody's going to cancel each other out except for this last term. And as the number of terms goes toward infinity, that last term that never gets crossed off is going to 0. And so this series converges to 1 minus 0, or 1. This is what we call a telescoping series. When you have a series where the denominator is quadratic, it's not the only case, but it's what we're going to see mostly this year. You should factor that denominator and then do the partial fraction decomposition, expand a bunch, and deduce what the infinite sum is. Here we go. Factor the denominator. Decompose this fraction into some partial fractions where each fraction has one of the factors. Multiply both sides by both factors so that it cancels out entirely on the left. and partially on the right. Let n equal -1, which will make this factor 0, so a times 2 equals 2, and a is 1. Let n equal -3 so that this factor cancels out. When n is -3, that's 0, and we have -2b equals 2. And if -2b is 2, then b is -1. So now we know how we can decompose this fraction into separate fractions. 1 over n plus 1, and when b is negative, this will be minus 1 over n plus 3. So write that out, and time to expand. When n is 1, this is a half minus a quarter, plus when n is 2, this is a third minus a fifth, plus a fourth minus a sixth, and so on and so forth. So the 1/3 never got canceled out. So our final infinite series will have a sum of 1/2 plus 1/3, and everybody else gets canceled out. Now there will be some terms left over in the end, maybe even several terms. But as n goes toward infinity, those last couple of terms that don't get crossed off are going towards 0. So as n approaches infinity, this series is approaching 1/2 plus a third minus 0, or just 1/2 plus a third. This series converges to 5/6. This slide is going to be fast because we've already talked about geometric series. You always have a first term, and then you always multiply by the exact same value for every other term. a1 plus a sub 1 r plus a sub 1 r times r again, plus a sub 1 r squared times r again. In other words, in summation notation, this is a geometric series, and it can be represented this way. What did we prove last week? If the r value's distance from 0 is bigger than or equal to 1, then the series diverges. But if it's less than 1, then the series converges. And we proved that the series converges to the first term divided by 1 minus the common ratio. As long as the r value is on this shaded part of the number line, it's a converging geometric series. If it's 1 away from 0 or more, then it diverges. All right, here's an example where you might not recognize it immediately as geometric, but it is. The first term was 7, and it was times a tenth. That term times a tenth, times a tenth. So the first term, a sub 1, the common ratio, and the power of n minus 1, right? Should it just be n? Are we not sure? Let's expand. We need our first term to be 7. So for n equals 1, to get our first term, we need this exponent to be 0, so that it's 7 times a tenth to the 0, which is just 7 times 1, which is 7. So it works out. In this case, we're starting a lower index of 1. The exponent on a common ratio had been n minus 1. All right, to get full credit for a question that says, does this series converge, and if so, what to, you need to identify the series as geometric, you need to identify the common ratio, and you need to compare it to 1. Is it less than 1 or greater than or equal to 1? Like this. For this problem, we would say this is a geometric series. The absolute value of r is equal to 1/10, and this is less than 1. Therefore, the series converges to the first term over 1 minus the ratio, which is 7 over 9/10, which is 70/9. One more example. You may or may not quickly realize this is geometric because the 7 is just a constant, right? And 8 to the n is exactly the same as 1/8 to the n. So there it is, our first term, our common ratio. So if this were a question and we're asked, does this series converge or diverge? And if it converges to what? We would say this series is a geometric series. You have to identify it as geometric. Then we're not just going to say that the absolute value of r is less than 1. We're going to identify what it is and compare it to 1. If you leave out any of that, you lose credit. So in this problem, the absolute value of r is equal to 1/8. And that happens to be smaller than 1. Therefore, the series converges to the first term divided by 1 minus the common ratio, which is 7 divided by 7/8, which is 8. All right, that's it. You should now begin the homework assignment.